Rightio, so here's an example of sketching motion graphs. We've got a ball bouncing this scenario, which does make it a trickier example, but it is one that does pop up in tests and exams. Okay, but please be rest assured that this is on the harder side. Generally what we're looking for here when you're sketching graphs of motion is the shape of the graph is the important idea. So in this example, we have a ball being dropped from a height of 1.4 metres above the ground, and it's caught at a high point of 1 metre. So what I'm trying to say there is that it's dropped, it bounces, and then when it reaches a velocity of 0 again, it's caught, and that's at a height of 1 metre above the ground. So clearly here the ball is losing some mechanical energy, so the collision here would classify as non-elastic. So to sketch the motion here, we need to make a few calculations. We need to determine how fast the ball was going just before impact and how long it took to reach the ground. And then just after impact, it must be going slower as it doesn't get to the same height. We want to find out that speed as well as how long it takes for the ball to reach its new maximum height. After we do that, we'll produce displacement time, velocity time, and acceleration time graphs for the motion. Okay, so in the just before scenario, I've done a little bit of a sketch. I really recommend a crappy sketch. It is worthwhile to sort your thinking out. So I've included a positive direction here. I've got the velocity just before it hits the ground, and I've put in that 1.4 metres. So what we know here is the initial velocity is 0 metres per second. The acceleration is due to gravity. Here I'm putting a plus sign just to indicate to the person marking this work that I've thought about direction. The displacement as well, plus 1.4 metres. Remember there it's from start to finish, so the displacement is down. And I want to find the final velocity. And I know it's going to be down, so I included that in brackets. So the formula on the formula sheet, v squared equals u squared plus 2as. But we can simplify that down because the initial velocity is 0. This is quite nice communication. It goes down to v squared equals 2as in this scenario, and it's very easy to make v the subject there. So subbing in, I find that the velocity just before impact was 5.2 metres per second down. Then finding the time, there's lots of different approaches we can take here because we know 4 variables, but simply using v equals u plus at, rearranging and subbing in, we find the time is 0.53 seconds for the ball to reach the ground. Okay, so moving on to just after impact, and this one is a little bit trickier because we've got the motion is up, but the acceleration due to gravity is down. So in a question like this in the test, I'll really be looking for positive and negative signs so you can clearly show me that you understand that these are vector equations and direction matters, and how we show direction is with directed numbers here. So again, a crappy little sketch. The ball's initially at the ground, it's just left, it's on its way up, and it reaches a maximum height where its velocity is 0, and I know the distance there is 1 metre. So I want to find that initial velocity. I know the acceleration is due to gravity and it's down, so it's positive. And here the displacement is negative. The start is the ground and the displacement is up, which is in the negative direction. Okay, so this is where most commonly I see errors being made. And while you still might get to the right answer, you have to fudge it a little bit. And we'll see why in a sec. Okay, so again, using the same equation, v squared equals u squared plus 2as. But here we know that v equals 0. Okay, so we can write down 0 equals u squared plus 2as. And then we get down to a little bit of a strange equation. We'll get u squared equals negative 2as. Okay, and at this step here, people freak out a little bit, might want to remove that negative sign, but we'll keep it, take the square root, because we find that when we sub in, the negative is really important out the front because it's going to make the quantity under the square root positive when I sub in using my directed numbers. Okay, so while it's a little bit pedantic, in a test question, I'm trying to differentiate between an A and a B. So this kind of accuracy, is indicative of an A student. Okay, and we get 4.4 metres per second up as the velocity as it leaves the ground, which is slower, so it's looking good. Again, to find the time, Subbing into V, take U on A, and remember that the initial velocity is up, so we have a negative sign here. So another little place where if someone didn't realise that, they'd get a negative time, and I'd see it in their working, but then their final answer, the negative would just disappear, and they'd just try and pretend it didn't exist. Okay, but time to reach the new maximum height, 0.45 seconds. So now I've got all the information to produce our graphs. So the easiest one to start with is the acceleration time graph. Okay, so very clearly I need to indicate a positive direction. So here I'm letting down be positive. I've labelled my axes, acceleration, units, meters per second squared, and I've given a direction there, so down. Again, so it's against time in seconds. So here, the acceleration is due to gravity, 9.81 meters per second down, and that's constant. Remember when we have vertical motion under gravity, the direction the ball's travelling in doesn't matter if we're ignoring air resistance. The acceleration due to gravity is always down. I've put a little hole here at 0.53 seconds because that's when it's bouncing, and I didn't give you any details of that bounce, but perhaps if I elaborated a little bit more on that, what it would look like is a very fast spike going a long way down and then back up, perhaps. Okay, to get that net force in the upwards direction to get the required change in velocity. But here, that's not the intent of the question. So just a little hole would be enough. And then it is caught at about 1 second. So I didn't get too pedantic here because we're ignoring how long it's in contact with the ground with. It is roughly 1 second here. So now the velocity time graph. This one looks a little bit stranger. So again with our labelling, velocity in meters per second to the 1, I assure you that's a 1, not a dodgy 2. And I've got the direction as down. Okay, so the ball was dropped, so we know it's starting at the origin, and after 0.53, it's just before it hits the ground, and we found it was travelling at 5.2 meters per second down. We see that we're joining those 2 points with a straight line, because a straight line in a velocity time graph, or a straight line, has a constant gradient, it's a constant rate of change, and if we have a constant rate of change of velocity, that means a constant acceleration. Okay, compared to maybe a car zooming off from the lights, if it started off slowly and then really picked up its acceleration, you might get a curve. Okay, but that'd be a rare graph to produce. So after the bounce, it's travelling at 4.4 meters per second up. So in our directional system, that's negative, but we see the same gradient in this line segment because the acceleration is the same on the way up as it is on the way down. Sometimes you might see these graphs with maybe a dotted line here. Sort of indicate that we don't have enough information to show what's going on, but we do know it changes from a velocity of 5.2 meters per second up down to a velocity of 4.4 meters per second up. Other things that we could look at in this graph, just to recap quickly, remember that the area underneath this curve represents a displacement. So the area underneath here should be 1.4 meters, the height it was dropped from, whereas the area here is the displacement from when it bounces to when it reaches its new maximum point. So this area should be -1 meters. So now the displacement time graph. So with our displacement, we need to set our 0 point. So here I'm taking the 0 point as the hand when the ball was dropped, hits the ground, comes back up to its new maximum height. So the maximum height was 1 meter on the second position there. So our displacement from the hand would be 0.4 meters. Okay, so looking at the graph now, we see that it starts at the hand, it bounces onto the ground at 0.53 seconds at a displacement of 1.4 meters below the hand, and then at the top of its next bounce, it's 0.4 meters from the hand. So what I'd really be looking for here is the shape of the curve. So you need to be able to explain why it curves opening upwards here. So with our acceleration due to gravity, initially it doesn't fall very far, but then as it's travelling faster and faster and faster, we see that the displacement is increasing at a greater rate. It's not a smooth section here because we have the ground changing the direction of the ball, and then when we see when the ball's no longer in contact with the ground, well, the displacement increases quickly initially because it's travelling quite fast upwards from the ground, then towards its maximum height, the displacement is not changing very quickly at all. And this should be a slope of 0 at this point. Could be possible perhaps that instead of doing a displacement time graph, you might graph the distance from the ground as it bounces. So in this scenario, again, it starts 1.4 metres above the ground. We know it's hitting the ground after 0.53 seconds. Then after 1 second, it reaches a maximum height of 1 metre above the ground. So here, thinking about the shape, so here it'd be more like coming down to a McDonald's sign. They're not a sponsor of this video, but anyway. Okay, so a little bit dodgy here, but initially it's not falling very quickly, so the distance from the ground isn't decreasing very quickly, much faster when it hits the ground and then bouncing back up. So if the motion was going to continue and we saw more and more bounces, what we would expect is a series of bumps that get less high. So the maximum is decreasing because the ball's losing energy each bounce, and then the time of the bounce would get smaller and smaller and smaller as it's not travelling as far. And then you might also like to think about what the velocity time graph might look like given multiple bounces.